Going on, class? This is lecture number 13. And we are getting into chapter 7. Chapter 7 is where we are. I hope you're doing good. Hope everything up to this point, chapters 1 through 6, have made sense to you and that the problems and assignments that you have been going smoothly. Let's talk about this idea of shear, right? Let's talk about this idea of shear. We were talking about bending moments and bending of beams when in our last lecture. I'm gonna share the screen with you. And when we think about, again, the shear that is happening across a cross section, I want you to understand that this shear force, right, that we often solve for is a shear force that's being experienced across the entire cross section, or distributed, if you will. This force is being distributed across the entire cross section. And there are a couple of different shears that are taking place, 2 different to be exact, right? There is the transverse shear, which is what you see here on the screen, right? All these arrows going down, right, represents what we call the transverse shear that is taking place on this cross section. However, there is a shear, and I've alluded to this in the past videos. There is a shear that is happening longitudinally along the length of the beam. And to help you visualize this a little bit more, take a look at these boards that are not bonded together, right? I showed this to you before with a stack of paper, but look at these boards that are not bonded together. As this concentrated force P is applied at the center of these boards, you're going to have a difference in the amount that each board sticks out. Why? Because along the length of these boards that are not bonded together, there is a force, a shear force, that is taking place, causing them to slip within each other. All right, they're slipping within each other. So this is what we can see when the boards are not bonded. Now imagine if these boards were all bonded together as if there were one beam, Well, in this case, you wouldn't necessarily be able to see the slippage. Why? Because they're bonded together and this entire cross section is acting as one plane. But that doesn't mean that the shear that is being experienced between the boards stops happening. It is still experiencing shear between the boards at this location, except in this case, that shear is being resisted by whatever bonding agent is taking place or placed between those boards, right? So we call it fasteners. Sometimes it's nails, sometimes it's glue, sometimes it's shear keys that kind of fit within each other. Whatever it is, there is something in between at this level of the cross section that is resisting the longitudinal shear. Does that make sense? Cool. I hope that makes sense to you. Now let's come to the document cam just for a second here. I'm going to show you a couple of equations. Now, again, as a reminder, we're in chapter 7, and this is our, if I'm not mistaken, our 13th lecture. And I want to remind you that in our last chapter, we were doing the flexural formula, which was MC over I. Yeah, remember that? This is the moment, right? This is the distance from the neutral axis. And this was the moment of inertia. Of course, that's the thing that may have taken you some time on the exams or on the homework to make sure you know how to solve correctly. This was the flexural formula. Now, in this particular chapter, though, we're going to talk about the shear formula, all right? The shear formula. And this is what you all should make sure you understand or are able to even memorize in this part of our course. All right, so shear stress, tau. Remember, this was just stress right here. This is stress, normal stress to be exact. This is shear stress, consistent with what we've had in the past with our equations. And this equals to V, the shear force, Q over I times small t. So again, this is shear This is moment of inertia. And put these in parentheses too, so you know that they're not part of the equation. Moment of inertia. This here is a thickness of the point we are looking at. And this is a new concept. This big Q is something I want you all to make sure you understand and conceptualize the best way you can, because this is a new concept, and it represents, let me just tell you what it represents. It doesn't really have like a name per se, but it represents the moment of the area, above or below the point of interest. Point of interest. All right. You're going to see more of T moving forward this chapter. I mean, not more of T. You're going to see more of Q in this chapter moving forward. You will see more of T as well. But for now, let me just go ahead and tell you that the equation for big Q is as so. Big Q equals Y bar prime and times capital A prime. That is the equation. That's the equation of Q. All right. Now, there are a couple of assumptions we're going to make before we get into some more of our application. But I want you all to understand these assumptions that are inherent in this process or inherent in this chapter, just like we had in the last ones. Assumptions / limits, if you will, to our application of these equations, these formula. So the first assumption that we're dealing with, excuse me, is that one, we assume that the shear is uniformly distributed across the cross section. All right, we're going to assume that the shear is uniformly distributed, right? There isn't higher amounts of shear or lower amounts of shear. Coming back over here, when we look at our screen share here, we're assuming that this shear is uniformly distributed. It's not like it's higher over here or lower over here or anything like that, right? It's going to be uniformly distributed across the cross section. Next thing that we are assuming, or rather is a limit for this, is that this is not accurate for wide flange intersections. All right, wide flange intersections, right? When there is a super wide flange here, and then there's a narrow web here, right? We're gonna have to do some interesting things to take place. And so it's not accurate precisely at that intersection. Now we will still be able to use it above or below, but precisely at the intersection for wide flange intersections is not going to be accurate. Now the next one is the edges. Get your edges of the cross section. This is a limitation of it. They are equal to 0. They're equal to 0. So if we're looking down at a cross section, let's imagine we're looking down at a cross section like this. We're saying that the value here and the value here are equal to 0. Even though you may have some forces throughout it and distributed throughout it, we're saying that at the edges, it's going to be equal to 0. And then number 4, again, a limit is that it is not accurate for short and flat members. All right, let's keep this in mind. You will see something like this, and we're going to show you how to solve for it, at least for in this class. But we just want you to know that this particular equation, this concept, and the way it's simplified in this course has some limits, has some assumptions, and we're going to deal with those in spite of in this class. So let's keep things moving. I think I'm going to do right now, before getting into the rest of the concepts, I'm going to do 2 example problems. So let's get into an example problem right now. You know, I'm going to look at problem 1. Problem 1, just to start off nice and simple, to make sure this concept is sinking in. Let me pull up on the screen the diagram for problem 1, so we all can take a look at it together. And so problem 1, it has a problem statement, and it reads like this: 7-1. It says, if the wide flange beam is subject to a shear of V equals 20 kilonewtons, determine the shear stress on the web at A, right? Web at A. Indicate the shear stress components on the volume element. All right. And that's going to be another thing I can just show you how we indicate that on the volume element. That's a 3D little cube. But it asks us to find, again, the shear stress on the web at A. So the first thing we want to be able to do is understand that to find the shear stress on the web at A, this is 7-1, we're going to need to know that this our equation is going to be like so: VQ over IT. Now, what are some of the things that we need to know, right? Well, it says T here, and the problem tells us it is on the web, So what does that mean in terms of T? Are we going to use the width of the flange or the web? Well, the question is very obvious. We're going to use the thickness or the width of the web. Next, it says V. Well, in the problem statement, it tells us that V is 20 kilonewtons. Then it also says, well, actually it doesn't say anything else, but we also know we're going to need this moment of inertia. Well, what is the moment of inertia? The moment of inertia is I equals the summation, right, of BH cubed over 12, right? We can do that in this case simply with this equation by taking the BHQ over 12 of the whole block and subtracting it. So the whole block would be 0.2. H would be 0.34 cubed over 12 minus, right? We're going to subtract the 2 sections here next to it. So 20 kilonewtons, 2.4. That's going to be 0.2, 0.8. Yep. 2 times 0.09. And then the height is 0.3. Let's go ahead and solve for that. 0.2 times 0.34. This is D. All right. This should be equal to 0.2501 times 10 to the negative 3 up to the 4. All right, that's our moment of inertia. And then the last but not least, we need to know what Q is. Well, Q, as I told you just a moment ago, let's make sure this thing is focusing well for us. All right, Q is equal to Y bar prime times A prime. All right, so here's how it looks. We have a cross section here, an I-beam cross section. This is a symmetrical I-beam. So it saves us any trouble trying to figure out where the neutral axis is. Why? Because the neutral axis is going to be right down the center, right down the center. That's the neutral axis because it's symmetrical, which means that from the top, the distance to the neutral axis is 34.34 divided by 2. That's 17. Yep, this is 0.17 meters. That's that height. Now, A, the point of interest, is right here at intersection. Now, granted, this is obviously an area where it's hard to be precise. It's not quite accurate. So that's why we're only looking at what they tell us. They told us to look at it on the web. That's why we use the 0.02, right? It's a tricky spot. But what we have to do is find out for y bar prime is the distance from the neutral axis to the center point of the area beyond the point of interest. So this is the point of interest, A. So we're going to go from here to here. Well, what is this distance right here from the neutral axis to the bottom of the web? Well, we know that to be 0.15. And then what is the half point distance of there to there? Halfway through the thickness of the web. Well, that's 0.01, 0.01. So the total distance y bar prime is 0.16. Next, we need to know what is the area of the point or the surface area beyond the point of interest. Well, we know that this is a thickness of 0.02, and we know that it is a width of 0.2, right? 0.2 meters. It's 200 millimeters, 0.2 meters. So that means that the area is going to be 0.2 times 0.02. That is the equation for Q. If you multiply that together, the answer we should get is 0.64 times 10 to the -3 meters to the third. All right, Q's dimension is cubed length. So this is meters to the third. So now we have all the values we need, and we can calculate it through. So let's calculate it through as so. Tau, and more specifically, we'll say tau at A, because that's the point of interest, is equal to 20 kilonewtons. So we'll say 20 times 10 to the third, just to put it in newtons, keep everything Newton meter, times 0.64 times 10 to the -3, and that's in meters, over I, which we know to be 0.2501 times 10 to the -3, times 0.02. All right, so let's calculate that to get an answer that we're looking for. 2, 10, 3 times 0.64. Well, if your calculator agrees with mine, what you should have in this case is 2.59. I'm sorry, 2.56. 2.56 times 10 to the 6 Newton meters, also known as PA. Or in other words, 2.56 megapascals. Megapascals is 10 to the 6. Now, it asks a little extra piece on this problem. It says, indicate the shear stress components on the volume element located at the point. So all that is saying is here at this point, if we were to show a volume element, it would look like a 3D box like this. All right, sorry about that. And basically on this 3D box, we have a shear going down here, shear going there. Underneath it, obviously, we'll have another shear And on this side, we have another shear. And all it's saying is here at this volume block, show that this shear is 2.56 MPa. And this one is here, 2.56 MPa. That's all it means by indicated the shear stress components on the volume element located at this point. All right. I hope that makes sense to you all, because it's very straightforward. We just use this equation here, and we need to make sure we had all of our components. Q, again, represents the moment beyond the point of interest, the moment of the area beyond the point of interest. So we had to make sure we got our y bar, which is the distance from the neutral axis to the centroid of that area, times the area of that area. And then that's how we were able to get Q and then calculate this number. So I'm going to do another simple one, though. We're going to do another simple one. And by another simple one, I simply mean 7-2. 7-2 in the book. And I think 7-2, if I'm not mistaken, actually uses this same image. So let's look at 7-2 just to make sure that we're understanding these components, right? It asks another question, slightly different. Let's look back over here at this image. Here's what 7-2 says, and you can follow along in your book. It says, if the wide flange beam is subject to a shear of B equals 20 kilonewtons, if I'm not mistaken, that is exactly what we just used. B equals 20 kilonewtons, right? If this is the case, determine the maximum shear stress in the beam. Same question, except in this case, they want the maximum shear stress in the beam, tau max. So take a look at this right here. I just wrote this out. V equals 20 kilonewtons, the same case that we had before, but now they want the maximum shear stress in the beam. So the maximum shear stress in the beam is still going to use V. It's still going to use I, the same I actually. It's still going to use T. But Q, in this case, Q is actually going to be a little different. Let me draw it like this. Let's still draw Q. All right. So here's what the maximum looks like. The maximum looks like this. I'm just going to show the top half of this TV. Very simple for you to conceptualize, but if this is the neutral axis here, instead of the maximum just looking at everything that's above a certain point, a maximum wants to use or determine the Q value for the entire area above or below the neutral axis. So Q, in this case, is going to be solved for this entire space. But let's go ahead and start by writing this equation out according to what we already know from our last problem, right? We already know that 20 times 10 to the third is what we're going to draw there. We already know from our last one, let's put this back out, that I is 0.2501 10 to the negative 3. So let's write that. 0.2501 times 10 to the negative 3. That's correct. Now, when we're talking about T, since we want to know the maximum, we're going to use this minimum value of T because it's in the denominator. So we're still going to keep the thickness of the web as 0.02. Now, the last thing we need to determine is Q. Now, let's talk about Q for a second. Q, in this case now, has to consider two different areas. So it's going to, instead of just being a straightforward equation, it's going to be the summation of y bar prime times a prime. That is what Q is going to be now for us. So we already know what it was when we were just talking about the top area, right? So let's go back to our problem. We know when we were just dealing with the top part, y bar prime was 0.16 and the area is 0.2 times 0.02. So let's start things off there when we're talking about the top part. 0.16 times 0.2, 0.02, plus, now what's the y bar for this place right here, right? We're going to go to place for the neutral axis to whatever the center of this section is. Well, we know that this one here is 15 overall, or 0.15. So what's half of it? Well, half of it is 0.075. That's the distance from the neutral axis to the centroid of that section of interest, 0.075. And then what's the area of it? Well, the area is 0.15 height times the width, 0.02. Y'all with me? Hope you are, because now it's just a matter of plugging and chugging to get the value of Q en route to finding our maximum shear stress. So Q should be 5 times 0.15. I invite you again, as always, to follow along with me. Q, in fact, we'll call this Q max because that's what we need in this case. The maximum Q should give you a value of 0.865 times 10 to the negative 3. And that is, of course, meters to the third, because that is the unit that we're in here. So right up here in this equation, we can go ahead and write that. 0.865 times 10 to the negative 3. There you have it. So now it's just a matter of calculating this all the way through. And if you do that, you should get 3.459 times 10 to the 6. And that's Newton's meter. Again, PA, which is what Newton's meters is. Or in other words, 3.459 MPa. That, my friends, is the maximum shear stress. And how do we do it as the max? Because we took Q not just for a section beyond a point of interest, we did it for the entire thing. So when it's asking for a point, 7-1 showed us we're going to look for Q for the area beyond the point of interest. That's what we're going to do. And when we're looking for the maximum, we're looking for the entire area above, or if we're looking at the bottom part below the neutral axis, just that portion. So I hope that makes sense. And those are two basic problems that illustrate this concept. Now, this next concept I want to show you is called shear flow. Shear flow, right? I can go to full document cam here. Shear flow. Now, shear flow is related to the shear stress, but we're going to denote it as a lowercase q. Lowercase q is our shear flow, shear flow. Now, the way we calculate shear flow is very similar to how we calculate shear stress. We're going to do V Q over just I. That's shear flow. VQ over just I, right? Now, I want y'all to understand that shear flow is what is going to allow us to determine what type of shear is occurring right here at that particular point. So if we're looking at a cross section and we know that at this point, that is where the member would want to experience some shear at this interface, right? Along the longitudinal length, shear flow is how we're going to calculate that. And shear flow is what we're going to use to determine how strong our bonding or our fasteners need to be in order to resist that slipping, as you can see here. So shear flow is a lowercase q, and it's going to give us the ability to solve for the number of fasteners. Let's stick with fasteners. Number of nails, the number of screws that are needed to resist that shear, that longitudinal shear. All right, so coming back here, the way we would do that is by this equation. This is the fasteners equation. So fasteners equation is this. The force per fastener, meaning the force that each one single fastener is strong enough to resist, equals Q, which is the shear flow, lowercase q, times the spacing of the fasteners. So let's do this again. Force per fastener Q is shear flow, right? And S is spacing, spacing of the fasteners. Go ahead and mark those, put a square around it, because you are going to definitely need to call on those in the future. So let me show you this diagram here. So let's imagine this is a wooden I-beam here. And you know that this wooden I-beam is experiencing, right, a load. And this load is due to some sort of force, but the way that it resists this load is due to the fact that these boards are nailed together, right? So it's not a monolithic, casting, single die cast I-beam, but instead it experiences some nails, or in other words, fasteners. So these are the fasteners. And then this here is obviously the spacing of the fasteners. Now I'm gonna show you what I'm talking about. We're gonna pull out another example right now. And that example is going to be 7-35. 7-35, a little later in the chapter, but we're going to be able to solve this together right here. It says here, the beam is constructed from 3 boards. Determine the shear V it can support. If the allowable shear stress for the wood is 400 psi, the allowable shear stress is 400 psi. What is the maximum allowable spacing of the nails? If each nail can resist a force, remember this is F, force per nail. If each nail can resist 400 pounds, 400 pounds. Now we're gonna have to do a couple of things here. We already noticed that this is not a symmetrical I-beam. It has 6 flange width here and a 10 here. So that means that we are gonna have to determine what Y bar is before we even really get too far down the road. So if we were to do that, I'm gonna go ahead and just do that. I won't narrate it much because I think that for the most part, you all know how to do this, but I'll at least show the calculations here. And 5.75. Mm-hmm. Boom. All right. If you get that, what you should get for Y bar for the overall cross section is 6.375 inches or feet. I'm sorry. Let me make sure. Did I do this in inches or did I do this in feet? Oh, yeah, this is inches for sure. Yep, this is inches. All right. Next thing we're going to need to get is our moment of inertia. Moment of inertia of this entire thing. Another thing that you should know how to do by now, but I will do it before you just so you can have the work to compare to yours. BH cubed over 12 plus A upon Y squared. All right. That's the equation. equals the height of the board. Times A, 1 times 12 times 6.375 minus, in this case, 0.75 squared, doesn't matter. Boom. The bottom one is 6 times 1.5 cubed. Area is 6 times 1.5. That's that bottom board. Boom. All right. So from there, we can determine that our I is equal to 1196.4375 as inches to the fourth. Just to the fourth. So we got this value, y, that enabled us to get this value. Now from there, we need to find out, it says the maximum shear. Well, the maximum shear is going to be correlated to the maximum stress. The maximum stress is going to have to be set equal to the maximum allowable, right, stress of the wood, which then should be equal to our equation of V Q, but it's just any Q because we're talking about maximum here. So it's going to be maximum Q over I. Thankfully, we already got that, over T, which we know is going to be the thickness of the web. All right. So let's start there. So going there, we're going to need to know what Q max is. Q max is. And because Q max may look different, right? If we're going up top versus we're going at the bottom because it's not symmetrical. Let's start off just getting a general Q max going up top, right? Let me do this on another sheet of paper so we make sure we have enough room. So we're looking at our cross section. It looks like this for the top part. Well, we got NA. You know that the height of that is 6.375. Now the thickness of this 1.5. And then we know also the height of this here is 4.875. In case you forgot, this is the Y bar we calculated. All right, so Q max is equal to, first the area of the top part, 10 times 1.5 times this entire one, so that's half of that. Or we can simply just say 4.875 plus 1.5 divided by 2. That's for the top part. Now we add that to the Q for the bottom part, which is, let's see, we know the width of this. According to our diagram, the width is 1 inch, 1 inch. So 1 times 4.875 times simply half of 4.875 And from there, we can get that Q max is 96.258 inches to the third. Inches to the third. So if we were to set tau allowable equal to V. Now did they give us V? No, they didn't give us V. V is what we don't know. Here's what we're supposed to determine, times Q max, which we now know to be 96.258 over I. We just calculated that. That's 1196. Let's say 1196.44. And then T is this thickness of the web, which is 1 inch. So 1. We know T allowable, so we said all this equal to 400 pounds. From there, we can solve for V. And if we were to solve for V, I'm sorry, 400 PSI, it's the wrong unit, PSI. Right, and what we get if we solve for V would be 4.97 kips. That solves the first part of the problem, was access to find or determine the maximum shear V it can support if it had an allowable stress of 400 PSI. Now access to find the maximum spacing. That's what we have to do next, find the maximum spacing. Now to find the maximum spacing, we're going to use shear flow, right? And if you remember, if you recall, shear flow is big Q, VQ over I. And then the spacing, the equation I gave you is capital F equals QS. Real quick, I'm going to show you something real fast. When it comes to finding the spacing, again, looking at lowercase q, VQ over I, we know our V, we know our I. In order to get the spacing, we're going to have to find two different Qs. Why? Because remember that this is not a symmetrical shape. So that means that the shear flow at the bottom here, because this is only 6 inches, right? 6 inches. It's going to be different from the shear flow at the top, where this is 10 inches. Not only that, but the distance from the neutral axis is different. So what we need to be able to find for this Q is a Q for this top and a Q for the bottom. Q for the top, Q for the bottom. So let's do it this way. We'll go ahead and do one at a time. Q at the top, remember, is Y bar prime, A prime for the top. So the distance to the top, I'm just going to write this out for you, is 5.625 times 10 times 1.5. That's what this is. And the distance to the center point there is 5.625. And that will give you 84375 inches to the fourth. That's the top. Q at the bottom. That would be 7.875. Right, you do the math of that. It's not drawn to scale here, but you will find that that Y bar is, again, 7.875 times 6 times the height of this, which is also 0.5, 1.5 inches, 1.5. And that will give you a value of 70.875 inches to the third, rather. I'm sorry, to the third, not to the fourth. So now we got those values. And so now what we're going to have for this little q, we're going to have a q at the top, which we've already determined to be 4.97. Is that what we got it as? 4.97. And that's times 10 to the third because it's not in a consistent unit. Top is 84.375. The I is 1196.44. Let me go ahead and write the bottom one here too. 4.97 times 10 to the third. 70.875. And the values you should get here is 350.62 pounds per inch. And then here it should be 294.52 pounds per inch. And so we use these little q's here to then find our spacing, because we can rearrange the spacing as F over Q. In the problem statement, it told us that F is 400. And then this is either T or B, depending on which spacing we want to know, the spacing for the top or the spacing for the bottom. And so the spacing for the bottom, for the top, let's start there, 400 over little q, so it's 350.62. That should give you a spacing of 1.14 inches to be precise. And then spacing of the bottom is 400 over 294.52. And those are our numbers to be exact, right? Those are the spacings to be exact. Don't forget that you had to find a different Q for the top and the bottom because they're not symmetrical. They're not experiencing the same moment about or beyond that point of interface, right? When we're talking about spacing, we're concerned with this point of interface because that is what the fasteners are holding together. But once we get the top and the bottom, we then get the little q of it by plugging it into VQ over I. Then we use this fastener equation over here to get the spacing. Hope that makes sense to you all. Definitely is straightforward, just knowing what equations to use and when. So I'm going to go ahead and stop this lecture right here. What we're going to do in the next video, we're going to maybe do one more example like this before we continue to take this concept further. But go ahead and pause, rewind, see if you get similar answers, and make sure you understand this concept in this lecture. All right, until next time, I will catch y'all then. Peace.